Here is a typical projectile motion problem. A football is kicked at a velocity of 10 meters per second at an angle of 37 degrees to the horizontal, and it follows this path, and eventually it ends up back on the ground. There are certain things we can find when we solve one of these problems. For instance, what is the maximum height of the football? How far down range did the football land? How much time was the football in the air? And finally, we can find out what was the football's velocity at the instant, just before it hit the ground. Let me show you how to solve this problem. The first thing we do is draw a pictorial representation. I will start by drawing my X and Y axes. X, Y. Here's a football. It's got an initial velocity, so V0 equals 10 meters per second. And it has an angle with the horizontal of 37 degrees. And it follows this path. It goes up, and it comes back down and hits the ground. Now let's write down all the information that we know about this football. First of all, let's look at the initial position and velocities. Initially, x0 is 0 meters, and y0 is also 0 meters. What about vx0? Vx0 is v0 cos theta, which is 10 cos 37 degrees, which comes up to be 8.00 meters per second. Now, vy0 is v0 sine theta, which is 10 sine 37 degrees, which is 6.02 meters per second. The acceleration in the horizontal direction ax is equal to 0, because we assume there is no air resistance. So we have ax equals 0 meters per second squared, and ay is negative g, which is negative 9.8 meters per second squared. So the initial position and velocity plus the acceleration during its journey. There are two important positions in this problem. First position is right here at the peak, at the highest position. Let's call that time t1. Now, t1, we don't know what that is. And x1, we don't know what that is. And y1, we don't know what that is. But y1 is one thing we want to find. That's the maximum height of the football. Now, vx1, we do know what that is. It equals vx0, because the horizontal velocity is constant throughout the journey. So it's 8 meters per second. And vy1 is something that we also know. At the very peak of its trajectory, the y velocity is 0. So vy1 equals 0 meters per second. The other important position in this problem is when it gets back on the ground. So let's say it gets back on the ground at time t2. And we don't know what that is, but that's something we want to find. That's the total time the projectile is in the air. Also, x2, we don't know, but we do know what y2 is. Y2 is 0 meters, because it's back on the ground. Vx2 is going to be 8 meters per second, because there is no acceleration in the x direction. Vy2 is something which we don't know, but we need to find out what that is. Then we fix up this thing. So this is all the information we have to solve this problem. So the first thing asks for, what were the horizontal and vertical components of the football's velocity? Well, we know the initial components of the football's velocity. Well, let's find the components at any time t. So part A, Vx at any time is Vx0 plus Ax times t. Vx0 is 8.00. Ax is 0. So we get 8.00 meters per second. So Vx is constant throughout the journey of the football. Now let's look at Vy. Vy at any time is Vy0 plus Ay t. Let's put in the numbers. It's 6.02. Ay is negative 9.8 minus 9.8 t. So this is Vy as a function of t at any time during the journey. The next part asks for, how much time did the football spend in the air? So we need to find t2. To find that, let's write down the y equation. Because we know the final position in y, and we know the initial y position. So let's write that down. y2 equals y0 plus v0y t2 plus 1/2 ay t2 squared. There's the equation. We know everything in this equation except t2. Let's put in the things that we know. 0 equals 0 plus 6.02 t2 plus 1/2 negative 9.8 t2 squared. We have to solve for t2. This is a quadratic equation, but you can see that every term contains t2. So we take out the common factor t2. So we would then get t2 times 6.02 minus, well, 9.8 divided by 2 is 4.9. So minus 4.9 t2 equals 0. Now here we have two factors. So t2 equals 0, or the second factor is equal to 0. So let's set those two factors equal to 0. So we have t2 equals 0, or 6.02 minus 4.9 t2 equals 0. Well, the first thing, t2 equals 0, occurs at the beginning of the projectile motion. The second one is going to occur at the end. So the solution is t2 equals 6.02 over 4.9, which is 1.23 seconds. So that is the answer to part A. T2 is 1.23 seconds. The total time in the air is 1.23 seconds. Now, next question is, what was the football's maximum height above the ground? So the maximum height is y1. There's two ways we can solve this. First, we can find the time t1, and then find the y position. Or we could use the equation which doesn't contain time. Let's first find the time t1. I wonder if you can think what t1 is going to be. If t2 is 1.23, what would t1 be? I think that half the time is t1, And then next half of the time is another t1. So 2 times t1 must equal t2. But let's solve it ourselves just to make sure. Let's try the purple. So this, by the way, is part B. Part C. At the very top, we know Vy1 is 0. So let's write down the equation for Vy1. Vy1 equals Vy0 plus AyT1. Let's put in what we know. So 0 equals 6.02 plus negative 9.8 T1. Solving for T1, we get T1 equals 6.02 over 9.8. And just as we suspected, is equal to 0.614 seconds. So 2 times T1 does equal T2, as we suspected. So now that we have T1, we can find the maximum height, Y1. We use this equation. Y1 equals Y0 plus V0y T1 plus 1/2 AY T1 squared. Putting in the values, 0 plus 6.02 times T1, 0.614, plus 1/2 times negative 9.8, 0.614 squared. If we work out all this, we get, for the maximum height, 1.8 meters. So this equals 1.8 meters. So Y1, the maximum height is 1.8 meters. That is the answer to part C. There's another way we can do this. We can use the equation that doesn't contain time. Let's do it over here. We would have Vy1 squared equals Vy0 squared plus 2AY Y1 minus Y0. We put in our numbers. So Vy1 is 0. So 0 equals 6.02 squared plus 2 times negative 9.8 times Y1 minus 0. You can solve this equation for Y1, and you're going to get 1.8 meters. That's another way to solve the problem. Part D says, how far downrange did it land? We're looking for x2. Well, we already know t2. So let's write down that x equation. x2 equals x0 plus v0x t2 plus 1/2 ax t2 squared. Putting in the numbers, 0 plus 8.00 times 1.23 plus 0 because ax is 0. And this is then, if you work it out, it is 9.8 meters. So this is 9.8 meters. So x2, the range of the football is 9.8 meters. Now, part F. What was a football's velocity at the instant just before it hit the ground? There are two components to the velocity. There is the horizontal component and the vertical component. So we have the horizontal component, Vx2. And then we have the vertical component. I don't know if it's going up or if it's going down. I suspect it's going down because it's going back onto the ground. But let's make sure. Let's look at our equation. We have dy2 equals dy0 plus ayt2. So that's going to be 6.02 minus 9.8 times 1.23. And that comes out to be negative 6.03 meters per second. Do you notice? Initial y velocity is 6.02. The final has the same magnitude, accounting for significant figures. We take two sig figs. It's the same magnitude, but it is in the negative direction. It's going down. So initially, the y velocity is going up at 6.0 meters per second. At the end, it's going down with the same magnitude. It makes sense. So this then, now I know I'm going to draw the Vy2. The vector is going to be down because it's negative. So I'll draw that here. So this is Vy2. I'm just going to put the magnitude here, 6.03 meters per second. So we add these two together and we get the total velocity, or the net velocity, or just the velocity. Right here. This is V2. And we have two components here. So V2 equals Vx2, a vector, plus Vy2, another vector. It's a vector addition. So to get V2, we make use of the fact that this is a right angle triangle. And we use the Pythagorean theorem. So V2 is square root of Vx2 squared plus Vy2 squared. And when we put in the numbers, we're going to get square root 8 squared plus 6.03 squared. And that comes out to be 10 meters per second. So V2 is 10 meters per second. So it left the ground at 10 meters per second. And when it came back to the ground, it was traveling also at 10 meters per second. Now we have to get the direction because we want the velocity. We have the magnitude. Now we need the direction. So we have to find this angle theta. So to get that angle, we use trigonometry. So we have tan theta equals opposite over adjacent, which is 6.03. Oh, by the way, this was 8.00. So it's 6.03 over 8.00. So theta is tan inverse 6.03 over 8.00. And if you work that out, it's 37 degrees. Note, I use the magnitude. I didn't put negative 6.03. That just causes confusion with your calculator because you're not sure what quadrant you're in. If you keep everything positive, then you know you're in the first quadrant and everything is easy to understand. So angle is 37 degrees. We can say 37 degrees below the horizontal. So 37 degrees below the horizontal. horizontal. So that's the velocity with which it hits the ground. We have a magnitude, 10 meters per second, and we have a direction, 37 degrees below the horizontal. So this is the vector. Notice, 37 degrees below the horizontal. When it left the ground, it was 37 degrees above the horizontal. And when it gets back on the ground, it's hitting 37 degrees below the horizontal. So when it hits back on the ground, this angle here is 37 degrees. So that is how you solve this projectile motion problem, when a projectile was launched at an angle. The next thing is to look at the graphs of acceleration, velocity, and position versus time. So let's do that. I'm going to have to get rid of some of this stuff. So we want acceleration. This is time, seconds. AX, meters per second squared. Then we have VX, meters per second. And we have X in meters. So we want these three graphs. So first of all, horizontal acceleration is 0. We're assuming no air resistance. So we can just draw a line. It's 0 throughout. Just draw a line along the t-axis. So that's the horizontal acceleration. We have 0 acceleration in the horizontal direction. That means the horizontal velocity is going to be constant. So it's going to be a horizontal line. And the value, or the y-intercept, is the initial horizontal velocity, which was 8 meters per second. So this is an 8. And then the position. So when we have a constant horizontal velocity, the position is going to be a linear function. It's going to increase. 8 meters per second means the position changes by 8 meters every second. So it's going to look like this. Just a straight line. And this time, 1.23 seconds. And this position here on the y-axis is 9.8 meters. That's the range of the football. So there are the three graphs in the horizontal direction. Now we want to do those three graphs in the vertical direction. The vertical acceleration is a constant value. It is equal to negative 9.8 meters per second squared. The acceleration due to gravity. So it's just going to be a horizontal line. Constant throughout, and this is negative 9.8. So when we have a constant acceleration, we have a linear velocity. Now it starts at 5, or what's it? No, it started at 6.02. So let me move this out of the way. I'll get my fine eraser. I'll get rid of all this. So this is meters per second. So the initial y velocity was 6.02. So I'll just call that a 6. Okay. Then it's going to decrease linearly. So it goes like this. At this point, when the Vy is 0, it's at the maximum height. And we saw that occurred when t was 0.614. So this time is 0.614 right there. And then it continues, it changes sign. It becomes negative. It starts going down from that peak and continues to be a linear decrease. And it gets down to here. And at this point, the y velocity, as we calculated there, it was negative 6 right here. And this time, where it happened was the total time in the air. That's 1.23. Now, the position function, when we have constant acceleration and a linear velocity, we get a quadratic position function. So the y position, it starts on the ground like this. The slope is equal to the initial y velocity, which is 6 meters per second. And then when it gets to this point, 0.614 seconds, the slope is 0 because the velocity is 0. So it goes like this. 0 slope, then it becomes negative slope and goes back down to a negative 6 meters per second slope. So it looks something like this. It's a quadratic function. Of course, this time of the peak is 0.614. This time is 1.23, and the maximum position was 1.8. So this here is 1.8. So these are the graphs for the problem. And this is how we solve a projectile motion problem when the projectile is launched at an angle. Thank you for paying attention.